This is a lesson on solutions. Most solutions are aqueous solutions, which means they're dissolved in water. So what is special about that? Why do we talk about that? Well, the geometry of water, it is a bent molecule, which means it has an angle of 104.5 degrees. That means it is a very polar molecule. You have the oxygen, the Lewis dot diagram. On this end, you have a large negative thing, end, because there's lone pairs of electrons. So that means this is a partial negative. The opposite side then would be a partial positive end. Hydrogen forms hydrogen bonds because electrons are pulled away and you're left with almost a naked proton right there. So that's a very positive side, that's a very negative side. It is one of the most polar molecules there are. If you dissolve an ionic compound, so you have an ionic solution, what happens is the water molecule is attracted to the ions, the anions and cations. It surrounds them and pulls them away. So if you have a sample of an ionic compound, alternating positive negatives, this is a positive ion, then on that corner, that side, the negative part of the water, which I'm going to represent as the V, attacks it, and when the force of attraction to the water molecules is greater than the ions with each other, it becomes hydrated. So it looks like this. Then the opposite occurs at the anion. The positive side attacks, and when its force of attraction, that force of attraction to the water molecules is greater than the ions, then it gets pulled away, and it is surrounded or hydrated by the opposite end of the water molecules. Some ionic, and this explains why some ionic compounds are more soluble than others. The greater the attraction between the ions, the more difficult it is for the water to pull the ions away. If there's a very weak attraction between the ions, it dissolves readily because the water molecules overwhelm the force of attraction. If you have a non-ionic, if you have a polar solution, a polar molecule has a positive and a negative end, so slight positive, slight negative, and another molecule would be attracted, and another particle will be attracted. I'm just going to put negative and positive, thinking those are partials, and another one would be negative, positive. So you got the alternating positive negatives, but there's going to be a positive negative on each side. Same thing happens with the ions, except the water molecules are attracted to the same molecule on the opposite sides. So the negative parts of water is attracted to the positive end, the positive parts of the water is attracted to the negative end, and it gets hydrated too, in the sense that the water molecule is surrounded, but it's more complicated because the one end has water molecules looking towards it, one does not. So compounds will dissolve only if it's polar. Water still surrounds the molecule. Non-polar molecules do not have a solution in an aqueous solution because there's no place for the water molecules to attract. If it's neutral, it's not that the water can't dissolve the particles, it's the water is more attracted to itself. So it looks kind of like this, and the water molecules are attracted to itself, positive ends attracted to the negative end, much more so than the nonpolar particle like that. So this gives you likes dissolves likes. Because nonpolar solvents will dissolve nonpolar substances because their attraction, the attraction of the solvent, is on the same order as the other things and just kind of mingle. So if you have just another molecule, you just kind of randomly do that. When we get to the point of talking about random and entropy, this become more apparent. The nature of solutions, I already mentioned some of these. Verbs and descriptions. So this is just terminology. Solvent is the major part, which I already talked about. The solute is the minor part. So if something's 30%, that would be the solute, and the other substance is 70%, that would be the solvent. A guy named Arrhenius, he'll show up often. He was a Swedish chemist in 1800s that did a lot of work. He proposed 3 different classes of solutions depending upon electrical conductivity. Electrical conductivity. Electricity if something's going to conduct electricity, what you need is to have mobile ions. The ions transfer, mobile means they can move, the ions means they can transfer electricity or charge from one wire to another. So what he did was he stuck a battery with a light on it into different solutions, and depending upon whether the light bulb showed up, glowed brightly, dimly, or not at all, he classified things. A strong electrolyte conducts a lot of electricity. The light bulb glows brilliantly. So it's due to a large number of mobile ions. So there's a lot of ions in the solution. There are 3 main types. There's the soluble salts, like salt, NaCl, copper nitrate, things like that. Strong acids, and there are 4 strong acids for this course. 4 common strong acids in this course: HCl, HNO3, hydrochloric acid, nitric acid, sulfuric acid, and perchloric acid, ClO4. And strong bases. In this course, strong bases are group 1 hydroxides. Group 1 hydroxides. Group 1 hydroxide, sodium hydroxide, lithium hydroxide, potassium hydroxide. All of these will ionize practically 100%. Weak electrolytes will conduct a small amount of electrical current because they have few mobile ions present. They have some ions, but not quite there. They include slightly soluble salts, and we're going to go over those in the next lesson, like barium carbonate, and there are a bunch of others. They dissolve, but not completely. 2, weak acids. Weak acids are all acids except for the 4 strong acids, and weak bases. And those are all bases except for group 1 hydroxide. So it's pretty cut and dry. You only have a very small part, a small percent ionized. So it's 5 to maybe 10% ionized. Not very many. And then the non-electrolytes do not conduct electricity at all because there are no ions present. So sugar is an example of this. Concentrations of solutions. We talk about molarity. Scientists do most of the time, chemists do most of the time talk about molarity. I'm talking about biologists. 1 molar solution is defined as 1 mole of the substance dissolved in or per 1 cubic decimeter or 1 liter of solution. The solution, which is important, we're going to talk about that later. Molarity equals moles divided by liters. If you have a 3.4 molar solution, M is the abbreviation for molarity, and it's read 3.4 molar, just like T. We have several sample problems. Not too difficult. You have 3 variables in the equation right here. You know 2 of the 3, you can solve the rest. Suppose you have 0.75 moles dissolved in 1.5 liters. So you have the formula they're asking for. What is the molarity? So you don't know the molarity. And you have 0.75 moles in 1.5 liters. Moles divided by liters, divide, calculator, 0.5 molar or half molar solution. You could have 2.5 molar divided by 250 milliliters. 2.5 molar, so you know the molarity, so that's 2.5 in front. And they're asking for the number of moles, so you don't know the number of moles, so that's left blank for the variable moles. And 250 milliliters. Well, 250 milliliters is not a liter, so what you have to do is change that, move it over 3 places, 0.25, cross multiply, and you get 0.625 moles. Another example, if you have 0.5 molar solution and 0.1 mole, what's the volume? So you're going to have the molarity, which they give you as 0.5, and they give you the moles, which is 0.1, which was given to you, over volume, which you don't know. Now, here's an easy trick. Switch. When you do this, you can cross multiply. Boom, boom. So 0.5 times V is the same thing as V times 0.5. So if you have the denominator, it's easier to do the math if you just switch those around. 0.1 divided by 0.5, and you get 0.2 liters. The last of these examples that we're going to do is if you have 4 grams of sodium hydroxide dissolved in 125 cubic centimeters. So you have 0.4 grams sodium hydroxide. Well, that's not moles. So you got to change it to moles. So 4 grams, not 0.4 grams. It's 4 grams. 1 mole over 40 grams. You get that from the periodic table for NaOH, sodium hydroxide, 2316(1). That's 40. So 40 divided by 40 is 0.1 moles, because the grams cancel. Now you've got moles and volume, so you can plug those in. Molarity, 0.1 moles divided by 125 cubic centimeters. Well, that's the same thing as 125 milliliters. So you still work it by milliliters and cubic centimeters, same thing, move it over 3 places, and you get 0.125, which turns out to be 0.8 molar solution. A lot of times they ask you how to make a solution of a given molarity. So if we were to do sort of a problem, what you do is you calculate the mass of the solute. So you got to find moles. It's the opposite of this problem right here. This problem here, you know the grams. What we need to do is find the grams. So you find the moles, and then add enough. This is very important when you do these. You add enough aqueous water to get the amount of solution. If you want, say, 0.5 liters, don't add 0.5 liters of water. Because if it's a concentrated enough solution, you're going to make more volume than what you had. So if you add a whole bunch of salt to water, the volume is going to be more than what you have. So what you have to do, say you know you need, let's go back up to here, you need to add 4 grams of NaOH to enough water to make, we wanted 125 milliliters of solution. If it's a weak solution, it doesn't really make too much of a difference. But if it's 1 molar or above, you might have 130 milliliters of solution, or 120, 150, depending on what the solute stuff is. Okay, last stuff is dilution. What we did above is how you do things with a solid. Now what you have is a concentrated solution, and you want to dilute it down to a weaker solution. The concentrated solution is oftentimes concentrated solution is often called the stock solution. Rather than have a huge jug of a solution that you're going to do experiments with, what you can do is you have a small thing and then dilute it down to what you need. So what you do is you want to dilute a stock solution down. The formula, the number of moles will be constant because it's the same number of chemicals, you're just adding water. So if you do molarity equals moles divided by volume, you solve for moles, That's molarity times volume. So what you have, the formula is molarity times volume of the stock solution equals the molarity times volume of the dilute solution. Molarity times volume is moles, so the number of moles of the chemical before is going to equal the number of moles after. The difference is you got more water, or whatever solvent you choose. So if you want 125 milliliters of a 0.02 molar solution, the abbreviation for solution is that, from a 0.5 molar stock solution, or standard, sometimes they call it standard. Plug and chug. The stock solution, the molarity of the stock solution is this. The volume of the stock solution is what you're trying to find out. The molarity of the desired diluted solution is 0.02 times the volume. Now the volume does not have to be in liters because the labels stay the same. It's going to be milliliters here, milliliters here, milliliters and milliliters. If it's liters and liters, you don't have to convert it back and forth. Just remember what the label is. So you do the math and you end up with 6 divided by 0.5. The volume is 6 milliliters of the stock solution. Now remember, you still have to do the same thing as you did before. So what you do is, how would you make a diluted solution? You would add enough water to 6 milliliters of the stock solution to make 150 milliliters of solution. So that is how you would do that type of problem. If you added 150 milliliters and the volume is additive, you would get 156 milliliters. Not that big an issue because it's so dilute. But if it's going from 0.5 molar to 0.1 molar, that would make a significant difference. That ends this lesson on solution.